Hey everyone, welcome to my channel. So today we're going to be reading a file. But the method I'm going to be using to read this file is by playing the part of the GNU kernel, also called Linux. So right before I started recording, I put a file called flag.txt inside my root directory, and the whole point of this video is basically how to read it. So here we go. So we're going to start off by identifying our disk devices. We're going to type in the command lsplk, and this is my solid state disk. The file system is usually partition 2 of your disk. So we're going to be reading data off here. And the way we read data is we're going to type in this command. Oh, we have to use sudo, and then this is our device, and then the byte size. And it's going to be loading this in 4096 chunks. That's what the byte size is. So if we wanted to, for example, if we wanted to load the first 4096 bytes, then we would use this command. We'll just try it. Here we go. We see a lot of zeros. The reason for this is the first 1024 bytes. These are all reserved for if you wanted to put a bootloader or something on there. These are all reserved for boot code or something. So we do not have anything there. After 1024 bytes though, that would be the super block. So if we want to read the super block and not just hex, we can use the command sudo dump that and then pipe it into less. So we get a nice user-friendly way to read it instead of reading hex code. So what we are looking for is basically, where is it? It is block size. So file systems generally segment things into blocks. And so in our case, the block size is 4096. I think this is the case on most file systems, ext4. Because, yeah, my file system is ext4 since I'm on a Linux. And we can see some other stuff here like inode count. This is how many inodes I have on my computer. Stuff like that. So anyways, we're going to take this and then okay, so the next however many bytes, we're gonna read. Okay, so we're gonna read this, and then the byte size is going to be. Okay, so the second block of my file system, this should have something called a block group descriptor table. I was confusing this with GDT, which is a global descriptor table earlier, and that was confusing me. So it's a group descriptor table, not a global descriptor table or just a block group descriptor. So we are going to read the second 4096 bytes of my hard drive. Not count. Okay, so we're going to skip one. And then we're going to pipe it into hex dump. We're going to add the -v flag so that we can read it better. And then we're going to suppress output, which is this thing. It's kind of annoying. I don't like this in the middle of my hex. So we're going to add 2 to dev null. Okay, now if we scroll up, we see a lot of zeros right here. There's a bunch of zeros, but there's also lots of filled in stuff, like 96. You can see random characters over here. So what this is the block group descriptor. So the first however many bytes here, this is offset 0. So this should be the lower 32 bits of whatever the heck this is. I don't know. But anyways, what we're looking for is the inode table. Inode stands for index node, and it's basically like metadata for a file. So a file will reference an inode, and that's how you know the permissions of the file. That's how you know basically everything related to the file. So we're going to look at, okay, so the first 8 are not very useful to us right now. So we're going to look over here. So this should be the inode table right here. And keep in mind that everything is little endian, and so these hexadecimals are basically just going to be reversed. So in this case, this number would be 000004 and then 96. Okay, so we're going to convert this 496 hexadecimal into decimal. So to decimal, here we go, and it is 1174. So this should be the location of our inode table. Keep in mind that these are blocks, which we previously discovered were 4096 bytes, and it is not the number of bytes, it's the number of blocks. So how we're going to read this, we're going to use the dd command. We're going to skip 1174 blocks, and we just want to read one block. Let's try this. And okay, we have some interesting data here. First thing to note, this should be inode number 1. It doesn't start at 0, it starts at 1. I don't like that very much, but this should be inode number 1. Each inode on my system is 256 bytes, and so this should be number 1. Number 1 is mostly reserved for like errors and things like bad blocks. And then number 2 is usually it should be the root file system. So from here to there. This is number 2. Inode index number 2. So we can look, here's the inode structure. And if we see this right here should be the inode. So the first 2 bytes. And 41ed, because again, it is little endian, 41ed. Okay, so let's analyze this. Down here, we can see, so 4,000, right, is a directory. And that matches up because it should be the root directory. And we can see the permissions from 1ed. If we convert this to octal, we get 755. And this should be our permissions. We can check real quick. Stat that. And there we go. This is the permissions of the root folder, and it matches up exactly with this right here. So we have a pretty good idea that we are looking for the root. We are looking at the root folder, but we don't have any path names or anything. So I'm gonna need to find out like what folders are in there. And the way we do this is there is an inode field called OSD2. Okay, it's this one. This is a block map or extent tree. So if we go here, the contents of inode .iblock, which conveniently is right here, we see this. So what I was doing for forever, and it was making me really mad, I was trying to fit it into this format, and that is only for ext2 and 3. So you will have to check your file system and make sure it is just make sure it is ext2, 3, 4. Just take note of this, because this was making me really, really mad because I could not figure out why it did not fit. Anyways, down here in ext4 we have an extent tree, and so the way we can parse this is we have a magic number over here, and again this should be at byte 28. So actually 28 in hexadecimal. So 20, and here is 8, so it should be right here. 0A F3, and we should have a magical number, F30A. And again, little endian. So we do have this magical number, and it's very, very clearly an inode now. And this, okay, so the first however many offsets, this is a header, just saying, hey, this is an index map, extent tree, whatever the heck. And we don't care about this stuff. What we care about is here. This would probably have to be our index node, because this is really the only number in all of these zeros. So let's just test our hypothesis and not even worry about this thing. Yeah. Wait, where'd the other number go? Wait, I copied it. Okay, there we go. So 00002496. 2 decimal 9366. Let's just test this out. Hopefully it works. Okay, we want to skip 9366. Oh, we're gonna use sudo and pipe this into, oh yeah, hex. Let's just two dev null, pipe this into hex editor. Wait, what was it? Hold on, I have to I forget these commands. Hex dump. CV. I can't type. Let's try this. Okay, we get a bunch of zeros, bunch of zeros, bunch of zeros. Oh, we found it. Look at this. This is my root folder. And here are all my folders. And we can see right here, flag.txt, that's what we want. All right, so now we have to read directory entries. And this is pretty simple-ish. So let's just read boot. Let's try boot. So we should have the name length. Actually, okay, we have the name right here. And I believe we're using this table right here. You may have to use this table for like older systems, but this table right here should work for me. So right before the name, we should have the file type. And let's just check this out. So boot, okay, so we have 1, 2, 3, 4, and then boot. 1, 2, 3, 4, and then boot. So this right here is boot. And before boot, we should have the file type. So this should be like 1 byte. Okay, right here. File type. And let's see. We have 2. And it is a directory, which checks out because I believe this should be a directory. So we have 2. And then before that, we have the length of the directory entry. Actually, wait. Yeah. Oh no, name length. So the name length is 4 because boot has 4 letters. If you did not have the name length, then it would be really confusing because the file system would not know how to interpret the name. It could be like the file type or something, so you have to specify that. And then 0004, that's the yeah, that's the name, or I mean the length of so the length of the file name is just 1 byte. No, it's not. Wait, yeah, it is. Name length 1 byte. And then over here, this should be 2 bytes. Length of the directory entry, which we get OC. Wait, what is that in hexadecimal? Yeah, it's 12. So I honestly have no clue what the length of the directory entry is. Oh, it's the entire directory entry. It's like the entire thing. Anyways, then we have the inode number, and this is 4. Yeah, this is 4 bytes long. So yeah, this would be the inode number right here. But what we really want to check out would be flag.txt. What we really care about is these 4 bytes here. This should be the inode entry. So I don't know what 17 is in hexadecimal, so 23. The inode right here is 23. So let's go find that inode. So each inode is at its own index, and each index is like 256 bytes. So what we're gonna do here is we have to convert 23. Let's see. So okay, so the inode started at 1174? Yeah, that was it. And now we need to add 23 256 byte chunks to it. So what we're gonna do is we're gonna take this down to 256. But because we're doing that, Now we have to multiply this by 16. So 18784. 18784. And now we have to add 23 to that. So that would be 807. Okay, let's hope this works. It should dump the inode of our flag.txt file. And that is not an inode. Something was wrong with my math. 18784. I'm just gonna add 23 to that. 18807. I thought I put that. Yeah, I did. Something is wrong here. 6. Gosh, I have to put a lot of self-trust in this. Oh, this is it. I think. Okay, let's just confirm that this is it. So, right here, we have A4, 81. 81, A4, whatever. And again, we can go to here to find the file type. So 8000 regular file, that's looking good. 481 to hexadecimal. To decimal. Would be, oh, sorry, octal. Ooh. Oh, I forgot, it's little endian. So it would be 81A4, 1A4. That's more like it. 644 is the permissions on this file, and let's just check that real quick with flag.txt. 644. We have confirmed it is flag.txt. So, now again we have to find the data. That was a little tedious last time. Yeah, let's just try it again. Okay, so to find the data, it should be around byte 28. And then the magic number is this many bytes long, 12. And, okay, so we've got rid of this, the magic header. And, let's see. Oh. It says it's 12 bytes long. And this is also 12 bytes long. Everything is 12 bytes long. Okay, so this would be the next thing. I believe last time it was the last 4 digits. Let's see. It wasn't this. This index node covers file blocks from this block onward. Lower 32 bits of the block number of the extent node that is the next level lower in the tree. Oh. I believe this is it. Right here. Let's convert this to decimal just to make sure. So it would be, hold on, let me get rid of this command. Okay. Which would be 01 4D 01 FF. And let's convert this to decimal. Ooh, that's a big number. I don't like big numbers. Let's hope this works. Making sure that it is the right one. I don't really know, but let's try it. Okay, this number, and we're gonna dump it. let's see. So byte size is that, and we're gonna skip this many. And please work. Please work. Here you go. Here is the file. Thank you to everyone who stuck around till the end of this video. If you learned anything new from this video, please like and subscribe. If you have any questions, please also comment down below. The links to all of the formats of the things we discussed are also down below. Thank you for watching.